Okay, let's start. Some new faces, all right? Okay, so welcome to the final lecture. All right, what do we do today? Firstly, we will finish our lectures, right? All the lectures about water and wastewater treatment. And then we'll go through all the solutions to our homework number 1 and number 2. And finally, I will very briefly talk about the exam, right? So that's the reason why everyone's here. Okay, water reuse, right? We have been studying water treatment, wastewater treatment, right? But we have not really connected these two. And we have learned that water treatment and wastewater treatment share some processes, right? Some processes like sedimentation, for example, and it could be coagulation as well, right? So in Hong Kong, our largest wastewater treatment plant, Stone Carter Island Sewage Treatment Works, is using what is called chemically enhanced primary treatment. So their coagulation using iron chloride, right, is performed for wastewater treatment. We have covered resource recovery from wastewater from previous lectures, right? Last lecture, recover energy from wastewater in the form of methane or even electricity, right? Even electricity. And we haven't talked about recover of other nutrients such as phosphate, right? But there are some research going on to recover phosphate from wastewater, right? So that can be recycled as fertilizer, right? Fertilizer. And today our final lecture is about recover the essential element, water, right? So we'll see that we can combine all these treatment steps to achieve the goal. We can recover different grades of water, right? From very pure, ultra pure water to some general purpose use water. Okay, so overview of water and wastewater treatment in Hong Kong. It's kind of review. So we import over 70% fresh water from Dongjiang, and we have some rainwater catchment, right? So that is about maybe more than 10% or a few percent. I did not quite remember quite clearly the number, but some portion comes from rainwater reuse. Rainwater use, right? Treatment process, then we get drinking water, and everyone knows that, right, for over 80% of the area in Hong Kong, we use seawater for toilet flushing. So that results a unique type of wastewater, right? So high salinity, about 10 gram per liter, right? 10 gram per liter, and that actually makes the water reuse quite difficult, right? Quite difficult. And so the majority of wastewater is saline wastewater, right? Of course, we can use membrane to augment the water quality, right? And also to use membrane to recover water. I mean, membrane as the essential or the critical component or treatment step, right? But the reuse process also involves other treatment steps, right? So it's not a standalone process. Right, TKO, we talked about this already, right? So 5%, right? This is membrane in, right? How can we recycle water? How can we recycle water? What's the difference between water and wastewater? Different compositions, right? You have different substances, different concentrations. That's a difference. That's a difference. And then, what is water reuse? It's actually to remove these substances, right, to reach certain quality, to reach certain water quality. And we have very different reuse purposes, from road washing, toilet flushing, irrigation, to drinking, right, and to the water used in semiconductor industry. It's a very high quality requirement. And a very simple process is to add a membrane, actual micro membrane after biological wastewater treatment, right? Biological wastewater treatment. This is what I've learned, conventional active sludge. So what we can do is to replace secondary clarifier, right? Use a membrane. Then you could get improved effluent quality. So what we can use this type of water for? Can we drink? No, right? Can we use it for irrigation? Irrigation, yes or no? Likely, very likely, right? Road washing, almost for sure, right? It can be used for road washing. And we can also combine the membrane process with the biological treatment process, and that is called MBR, right? Membrane bioreactor. And that is the technology we plan to use in Shawu effluent pollution plant, right? But that capacity is about 60,000 cubic meter per day. Still a very small percentage, about 2.5%, right, of the water we use. We can learn a little bit more from this video about MBR. So originally it's quite expensive, but now it's becoming more and more affordable, and you can see many places are utilizing this. Here. So the rest part of the video is introducing the membranes produced by the company. Right? So let me ask you this question. Can we use MBR for our saline wastewater we use? Can we? Can we? Yes or no? Yes or no? So we should put this into the exam. So technically, yes, right? We can do that. But the result is you end up with some saline water, which is not very useful, right? So how can we use saline water for what? Right? We don't know. So that's difficult. That's difficult. Right. So one example, I visited this site a couple of years ago in Guangzhou. Right. So it's a fully underground plant. So above the ground is almost like a garden, right? Very beautiful. And all these treatment tanks are underground. And the process is what is this? What is this? AAO, right? Anaerobic, anoxic, and then MBR. So the effluent quality is quite good. This is the membrane tanks, and this is the effluent, and these are the hollow fiber membranes used in that plant. Okay. And this is, I believe, a renovated plant, right? So it was built in some remote or suburban areas, but when the city grows, right, it becomes in the center of the city, and there's a lot of more population to serve. So the treatment capacity needs to be increased, and also the effluent quality needs to be upgraded. So many wastewater treatment plants like this type will adopt MBR, right? And some are considering build the plant fully underground, because it's already in the center of the city. Right. So what we're doing in Hong Kong, this is probably the first, right? First, I believe Bo also introduced this to you. MBR is used there, right? So a few concepts. So what we are doing now, right? So this is a leader system, water treatment, use, wastewater treatment, and discharge, right? And what we envision for future water or wastewater treatment will look like this, right? Feed water treatment, use, right? Use. Then resource recovery. Not only water, but also nutrients, but also energy. Okay. For water, we have different use, potable, non-potable. okay, potable, non-potable, and then we could send them back into aquifer. Okay, aquifer. The example we're going to introduce. So it's not a linear system anymore. It's more like a cyclic. Okay, cyclic system. This is called the fourth water revolution. As briefly mentioned in the video, right? This is probably regarded as the most feasible way to produce potable water. Okay, potable water, MBR, or at least some membrane, right? Arterial, micro, or nano filtration membrane, and then reverse osmosis, and then UV disinfection, and then you drink that. But that's direct potable reuse, right? Direct potable reuse means you drink from the outlet, right? But we have now more common is indirect potable reuse. What does indirect mean? We treat them again, right? We send the treated water back into our natural environment, such as aquifer or some reservoir, right? Then we treat all this water again using our water treatment process. So that's indirect water reuse. Right? But this is likely the most promising process trend. Okay, process trend. Some are researching nanofiltration ahead of reverse osmosis. Okay, this is not a new concept. Okay, it has been practiced for perhaps 50 years already. Right. So this is the story of Singapore. Many of you have heard, I believe. Right. So Singapore is now recycling 40% of its wastewater. That's an extraordinary number, 40%. And by 2030, their goal is 55% of all the wastewater they're going to recycle. And they call that water new water, right? New water. We have a video. What is new water? %, 55% by 2030. So that's their goal. What's the treatment process? So it's very standard. Okay. You started with the micro arterial filtration, then reverse osmosis and UV disinfection. Okay. And typically UVC, shorter waved, about 250 nanometer in wavelength. So very strong energy to kill pathogens. Right. As we said, the pathogen control is very important in water treatment. Okay. And so this graph, this is a paper actually published in Nature in 2008, some 16 years ago already. Right. Talking about the promising technologies for water treatment. It has been cited perhaps nearly 10,000 times already, right? So what we should do, for example, this part, now it is using UVC. So how about photocatalyst, right? How about solar-powered disinfection technologies, which could be cheaper to use, right? So that is where the innovations are being made. And also regarding this part, so how about other membranes, right? Reactive membranes, not only filtration but also reactions, right? So some research are going on. Another example is Orange County in California, right? So very extraordinary example, 100% reuse, Orange County. A very similar process, right? A very similar process, microfiltration RO, and then UV. So it's almost like a standard treatment procedure. And what they do, they inject the water back into the aquifer, right? Or to the spreading, or to the injection wells, or to the spreading basins. If you go to Orange County, you will see this type of spreading basin, quite large. Okay, this is the treated water, and the water will infiltrate and go back into the aquifer. Or the water is injected through the injection wells to the aquifer. Okay, and then it will be pumped out for treatment again. So that's indirect potable reuse, right? the 100% reuse Orange County. Of course, there are some other examples in the world. Our final slide is a TED talk, but I guess do you want to watch now, or you want to go back home and watch or never watch? But it's a very good video. The professor David Sedlock is quite a well-known water expert. He's now working at the UC Berkeley. He spent 3 months with us before, I believe, before COVID, IPolU, right? And this TED talk tells us the four so-called water taps. Right? What are the four new water sources? Right? This will mean seawater desalination, water use, stormwater, water conservation. Right? It's very insightful presentation. I would definitely encourage everyone to watch. It's about 10 minutes or so. Let me think how long. I'll skip this. Okay, let's take a break. That's the conclusion of our all the lectures. So go back home and watch this. It's quite insightful, especially after you have learned the subject. Okay. Right, please submit your homework. We're going to talk about solutions, so you better do that before we. What I would do next is to go through all the homework problems. It's very difficult to see, right? Right, I'll explain anyway. So the first problem is about the calculation, right? Calculation. So what do we use? Iron sulfide, right? Iron sulfide, and you get actually a little bit different from this one, right? So it's precipitates. It's precipitates. Right? So that's an equation. That's an equation. Iron sulfide reacts with water. You get iron hydroxide as precipitates, and some protons are produced. Right? Proton produced. So a little bit of different from this equation. Right? But sometimes you have this hydrated chemical compound. It comes with some water molecules, and that's fine. Okay. And then for the second step, anyway, I haven't finished. Right? So this is 1 mole, right? Iron sulfide. You get 2 mole iron hydroxide, right? And that's easy to calculate how much iron hydroxide produced. So it's 10.7 milligram per liter. 10.7. This is the molecular weight, right? And you get 2 mole of this. This is wrong. Okay. Substrate is wrong. Okay. But it's 1 mole. Oh no, sorry. Right. So this is wrong. Okay. So this step 1, step 2. Any question? Anyone has any question? No. No. Okay. Then for the third step, you are asked to calculate alkalinity, right? Alkalinity consumed. Basically, here you have 6 mole of proton produced, right? That corresponds to 3 mole of carbonate, right? 3 mole of carbonate. Why? Right? So that's 3 mole of carbonate. But in terms of alkalinity, very importantly, you have to write the correct unit, right? What's the unit of alkalinity? What's the unit of alkalinity? Milligram what? Calcium carbonate per liter, right? So that's the unit. Milligram calcium carbonate. So 3 more. That's 3 more calcium carbonate. 3 more calcium carbonate. And molecular weight is 100 calcium carbonate. Right? And you will get 15 eventually. 15. Question? Any question? So notice this step. If no question, I'm going to move to the next question. Next problem. So this part may be a little bit confusing. But anyway, right? Anyway, 1 mole of iron sulfide corresponds to 3 mole of calcium bicarbonate. Right? So that's the relationship. 1, 2, 3. Then the alkalinity. So if you have 20 milligram per liter of this, and it's 300 gram per mole, right? You get 3 mole of calcium carbonate. What is the molecular weight? Right? So the number is 15 milligram per liter. All right. If no question, we're going to move to problem 2. Okay. So problem 2, it's very important for you to start with the. So we have this problem in class, right? A diagram, right? A diagram. So the fate at 8 mgd. Aluminum sulfide is 1 mgd, right? Effluent. What is the effluent? It's a combination of the two, right? Combination of the two. Then you have a very good sense of mass balance per liter. And here, what's the concentration? Aluminum sulfide. 0, right? 0 gram per liter aluminum sulfide. You can establish a mass balance for aluminum sulfide. The first step here is actually the mass balance. The mass balance. The total, the effluent is 9 million gallon per day, right? 8 plus 1. And then the concentration is 8.9 milligram per liter. Okay, milligram per liter. And what is the second problem? Quantity of aluminum added. That's easy, right? That's easy. Quantity, concentration times flow rate, C times Q. C times Q. But the trick here is you're asked to convert the unit into pounds per day. Okay, pounds per day. And third dimension. All right, so dimension. What is dimension then? What is dimension? So we talked about V. If you're asked to calculate V, you should think what equation? HRT, right? What is HRT? Right? You always think of this equation, HRT. And what do we get? Residence time 60 seconds. 60 seconds. And you want to calculate V. Of course, here this step is important. Flow rate, right? The flow rate is 9, it's not 8. That's important. Otherwise, you will make a mistake there. 9 million gallon per day, and you get V 835 cubic feet. Okay, cubic feet. It's a cube. It's a cube. So you can calculate dimension, right? The length, width, and height is the same. 9.4 feet. 9.4 feet. Okay. In the exam, it will only be international unit, so don't worry about the conversion. Okay. And then the impeller, right? Impeller. That's an equation from the lecture note. Okay, lecture note. And the final problem is power input. Power input. The same equation in the lecture note. G square root P and viscosity times the volume, right? Times the volume. Okay. And you get a unit of watt, 2124 watt. Okay. And what is this step? This step is to convert the unit from watt into horsepower, right? Horsepower. This step. So 1 watt is 0.00135 horsepower. So this is unit conversion, and then the efficiency 80%, right? So 80% should be divided by 80%. Then the required power input is 3.56 horsepower. Okay. Question? Okay. So I guess some of you may have made a mistake here, right? The Q. So everyone is okay. We move to next. Okay, so next, I believe it's quite easy, right? Rectangular car fire, you have the dimension, the length, the width, and depth, and then the flow rate. Okay, but that's a total flow rate for the 4 rectangular car fires. Right? So 40 million gallon per day, the number is for 4. For each tank, you should be divided by 4. Okay, overflow rate. Okay, so this is basically to test your understanding of the concept. What is overflow rate? What's the equation? Q A, right? Okay, A. Basically, A is length times width. Okay. And the second, detention time. All right, right? Just here, detention time, HRT, V divided by Q. And then horizontal velocity. What does horizontal velocity mean? You have a tank, right? So that's this direction, right? It should be Q divided by this area, right? And this is height times width. And wear length, that's also from lecture note. Okay. What is this? What is this called? Wear what? Wear loading rate. Whatever, just check. Okay. But anyway, you can actually tell from its unit, right? Unit. This is the unit of Q, gallon per day. Feet, unit of length. Right? So that should connect with Q. Right? Therefore, the length is Q divided by this rate. You better draw a diagram like this. And first, that's easy. But pay attention to the Q, right? So this is for 4 tanks. And therefore, you have to divide this number by 4 to get the flow rate for each tank, because the dimension is for 1 tank. Right. The same for hydraulic retention time. The flow rate should be 1/4. 1/4. That's 10 million gallon per day. 10 million gallon per day. Right. third horizontal velocity is q divided by width times height, right? Okay, right. And this is also the conversion of unit, feet per minute. And finally, the wear length, q divided by the rate. Right. So this number is the total length for 4 tanks, right? Because here q is 40. That's for 4 tanks. And for each tank, the length should be divided by 4. Then you get 333.3 feet. All right. So let me pause here. Any question? No? The crystal clear. So what's next? Okay. The next problem is settling. Settling. And you have all this number and the particle settle, right? You have the horizontal velocity, you have the dimension of the tank, and you're asked to calculate overflow rate. Overflow rate. So basically here, for the first problem, we consider the time, right? The time is the same, right? Horizontal direction and vertical direction. Traveling time. So tell me, what's the time for the horizontal travel direction? What's the time? It's a divided by, right? Vertical direction. What is that? Right? So basically, you're calculating this number. For the second question, right, from the graph, you see that the length is not long enough for the particle to settle, right? So you need to increase the length. And how can we consider? And the first step, we calculated the critical velocity or overflow rate, right? So what is VC? This is actually VC. What is VC? Critical velocity. By its definition, what is that? So tell me. Overflow rate definition. Q divided by A, right? What is Q then? What is Q? Q is VF times what? Times height, C times width, right? Right, that's Q. What is A? A here it's the length you want to know and the width, right? And the width. Basically, you can cancel this and you get L, 7.5 meter. Okay, VCA is calculated from the first step. So you can have different solution. The table, this table is not relevant. Okay, the table is not relevant. Okay. This is an example. This is a problem from textbook. Okay, textbook. You know we have a textbook, right? Okay, so go to read the textbook. All right, question? It's not very easy to understand from here. Okay, but think about this. This will help you to understand how we get the number. Right, the definition of critical velocity or overflow rate. Okay. Move next. Right. Problem 5, current Cosenyi equation. Right. I do not have the detailed step, but basically plug in all the numbers. Right. But be careful about the unit, right? The unit you choose. Head loss. So eventually you're going to get a number with the unit of length, right? Meter. That is the unit of head loss. Right. So as an engineer, you should always put the unit next to your number, and you can check whether your calculation is correct or not. Because if it is correct, you're going to get this exact unit. Okay, exact unit. I believe the number is 0.34. 0.34. Do you have any question? No? Not very difficult. Fundamental concepts. Right? You want to move to homework number 2? Okay, so last chance. If you haven't submitted homework number 2, please do it now. Homework number 2. All right. First one is easy, right? You have 7-day BOD. You have 7-day BOD, and you're asked to calculate BOD 6. Right? So generally we use BOD 5, right? BOD 5, and also BOD 10 and BOD L, and we have the key 0.15 day, right? And here, right? So we corrected the typo in the lecture notes. Okay. Even we didn't correct it, you should know this because check the unit, right? Check the unit. K, the unit is per day. Is per day. T is day. Per day times day should be units, right? It's not K over T, it's K times T. And right, so BOD 7 is 210. 210, you get a BOD L first actually. That's BOD ultimate. It's 323 milligram per liter. Right? So you get an ultimate BOD first. And then BOD 6, that's easy. You just plug in 6. BOD 10, you plug in 10, get the two numbers. All right? Anyway, this is 323. Okay? 323. That's easy. So is your number right? Almost. Almost. Some calculation mistake. All right. So how about your numbers? You still remember? No? The same? Okay, good. So that's easy. How about problem 2? Okay, problem 2 is, right, the key is to write. The key is to balance the equation, right? The key is to balance the equation. Theoretical OD. Theoretical OD. But luckily we do not have nitrogen here, so the problem is easier, right? Basically you're calculating COD. NOD is 0. So what if we have nitrogen there? What if we have nitrogen? What is theoretical OD? What is theoretical OD? What is theoretical OD? COD plus NOD, right? COD plus NOD. And here we do not have nitrogen, so we're calculating here, right? This part. What if we have nitrogen in the chemical formula? Eventually, nitrogen will become NO3, right? NO3, nitrate. Oxidation state from 0 to positive 5. Right? The first step, if you calculate theoretical COD, you get ammonia first, right? And then, right? Okay. So pay attention to this. How to calculate theoretical COD, theoretical NOD, and theoretical OD. Okay. The very first step, you have to make this equation right. Balance the equation right, right? Everyone knows how to do this, right? Middle school chemistry. Okay. Middle school chemistry. You start with carbon, then hydrogen, then oxygen. That's an easy one. Okay. And also in terms of molecular weight, I'm not going to give you what is carbon atomic weight of carbon, hydrogen, oxygen. You should remember that. That's too fundamental. Okay. All right. Carbon 12, hydrogen 1, oxygen 16. Right. So molecular weight 839. Theoretical OD. Right. Right. The answer here, the unit is not the precise. It's not correct. What's the unit? So tell me what's the unit? Gram what? Gram oxygen per gram whatever chemical, right? Right? Gram. What do we have? Grace. Okay. The unit is important. If you do not write the unit correct, some points will be deducted. Okay. Okay. Any question? Any question? No. So far everyone is okay. I just randomly check a few. Yeah. It appears to be easy, the problem. The problem number 3, what do I have? We have the Q, right? Q, 36,000 cubic meter per day, and then BOD, that's fluid concentration or influent concentration. Right. So here we have a constant BOD loading. Someone asked, what is BOD loading? That is also a basic concept. So tell me what's the equation of BOD loading? What is BOD loading? What is the unit? Gram per cubic meter per day, right? It's Q times say whatever you call it, or S0, right? Divided by V, right? Divided by V. Cubic meter per day times milligram per liter divided by cubic meter, right? So that exactly the same unit. That's BOD loading rate. And the flow from the aeration tank is distributed to 4 clarifiers. All right, the first question, what is the volume? What is the volume? Here, right, BOD loading. You have BOD loading, you have the Q, you have S0, and you can calculate V, right? Second step, aeration time. What is aeration time? What is aeration time? Theta 1. Theta C or theta? Theta C or theta? Right, aeration time. Aeration time, right? How long the water stays in the tank. The time that the water is aerated equals the time water stays in the tank. So it's theta, right? So it's HRT or theta. It's not theta C. What is HRT? Right? V divided by Q. You have got V here, and you have Q. And food to micro C from C, that is to test your understanding of FM ratio. What is FM ratio? What is F? Food, right? Food is Q times S0. What is M? Microorganism, right? XV times V, right? XV times V. So you have V already from step 1, and you can calculate XV. You have right. So you're asked to calculate XV. FM ratio 0.3 is given. Right? So D, operating / age. What is this? So this is theta C, right? So this is theta C. And which equation we should use? Theta C, we have a number of definitions or equations, right? How theta C is defined? How theta C is defined? Total microorganism over removal rate. That's the original definition, right? So it's Q minus Q what? QW? Let me all right, it's QW XW plus right QE times XE. Right? Huh? Yeah, QE is Q minus QW. Right? It's the same. And here Q is much larger than QW. Right? So so let us look at solutions. So first, 2,700 cubic meter, right? The second, theta is 7.2 hour, and C 2,000. Right? Okay, so these are very fundamental concepts, and these equations will not be given in the exam. Okay, if they are tested, but they may not be tested. But I can tell you that they will not be given because it's too fundamental. Okay, You should know what is FM ratio, right? Otherwise, why come here? Okay, theta C. Right. So here, for this part, QW, we do not consider, right? And this 9,000, right? 4.25 day. Right. So we do not know QW, but the whole part is known. It's 1,000 kilogram per day is given, right? Okay. Right. Problem E, and we have 4 equal clarifiers. For each clarifier, upper overflow rate, flow rate, overflow rate. What is overflow rate? Q divided by A, right? Q divided by A. And if for problem F, you have the depth, you have the area, so you know the volume, right? And you have the Q. Then you have the retention time, V divided by Q. V divided by Q, right? You see, we are testing the concepts over and over again. What is data? What is HRT? What is overflow rate? Right? All right. So no problem. Okay. Problem 4. I do not remember. Do we have this in our class? No. Okay. So it was one of the exam problems. So perhaps for undergraduate students, not so many students had answered this correctly. Right. It was a little bit confusing. Right. So we'll see how. A little bit tricky. What do we have? Determine kilogram per day suspended solids to be wasted. Right. To be wasted. So that is QW times XW. Right. QW times XW. We know what aeration tank volume. So we know V MLSS. Right. MLSS. And influent Q. So we know Q. And so percentage, volatile suspended percentage. What is this? What is this? Right? MLVSS over MLSS. Volatile suspended solids over suspended solids. So that is 67%. And we have BOD, S. We have S. And we have desired food to microorganism ratio. Desired food to microorganism ratio. Right? But pay attention to the unit. I don't know if you have realized what is the unit of food to microorganism ratio here. So it's gram BOD per day per gram VSS. Okay. So here it's VSS, volatile suspended solids, right? That's a unit. Then if you write the equation F, that's Q times S0 microorganism, should be ML VSS times V, right? This is known, this is known, this is known as well, and this is desired, right? So you have a desired what? MLVSS, right? Desired MLVSS. And if you know desired MLVSS, you have what? Desired MLSS, right? And the problem asks you to determine the kilogram per day SS, suspended solids to be wasted. Right. So this is desired, and you have the current. The current. What's the difference? The difference is the amount to be wasted, right? So now you have a value, and you waste some, and you get desired, right? So you get desired value. And basically, that is how we solve this problem. Okay? Right? So this is desired, 0.3, right? 0.3. Then total amount. This is X. This is this part. Okay, the entire part. Entire part. And This is part wasted. This is current you have. Right? It's about 3,000. How many of you have got this? Would you raise your hand? You too? You? You? Yes? So almost everyone? Good. Okay. Question? Question? No? So you have to be very familiar with what is FM ratio, right? The concept. Right. Final problem is the use of the Wells equation. Um, I do not have much to say about this. I just want to remind you the unit, right? Always the unit. If you pick international American unit, so you have to pick the corresponding parameters from that table, right? And be very careful. And if you do not know, for example, what is this, check its unit, right? It's, what is this? Specific velocity, right? Specific velocity because you have a right. 26 something. Okay. 26.8. All right. Okay. All right. Any question? Any question? So how many points you are going to get out of 100? 100. Whoa, impressive. All right. So each homework will account for 15%. 1.5. Right. So it will be converted into 15-point scale, and the exam will be 70%. 70%. And generally, we're not going to test empirical equations in the exam because that's easy, right? So the purpose of the exam is to test your understanding of the fundamentals, the concepts, and use of some of the concepts. Right? Okay. So, any question before I move to the next topic? No? All right. Okay. All right. Next, we're not going to have a break. Okay. So we briefly talk about exam, then we finish. All right. If you want to go to the restroom, just go by yourself. Okay. Feel free. So the exam, very brief. You will be given 3 hours. I think you have enough time, more than you need. The exam, I believe 6 problems. I believe 6. So fundamental concepts, essential. It's like a Q&A 50%, around 50%. Calculation based 50%. Water to wastewater, half to half, almost. Right. So all the 12 chapters will be covered, but you know some are important, some are less important. Right. Calculations. Right. You have done some calculations. So the calculations will be similar to the homework and in-class practice problems. Perhaps one problem is somehow difficult, but not very difficult. If you understand the concept very clearly, you should be able to solve most part of it. Maybe one part, last part is a little bit tricky, but it should be okay. The level of difficulty is similar, right, to the I think to the homework problems or in-class practice problems. And then right, basically the calculations will come from what you have been practicing, right? All this. So you should practice the in-class practice problems and homework problems again to be familiar with them, and then take a look at the previous exam papers. That should be helpful, right? Should be helpful. And regarding the concepts, so you can take a look at the previous exam papers, right? We only have all these concepts, right? Theta, theta C for the microorganism ratio, right? So we can start from the list. Introduction to water, right? Introduction to water. Think about, right? All this. In each chapter, there are some key concepts and some learning outcomes, right? Learning outcomes. Calculation, fluctuation, right? Right. Very fundamental concepts from each of the chapter. Okay, so there are indeed many concepts. But I believe it should be okay if you have done the in-class practice and homework on your own. If you are able to finish all this, it should be okay, right? It should be okay. Okay, any question? Any question? No? Yeah, please. Hmm? Right, right. It's not MLVSS, right? You are talking about this, not this, right? Right. So this is sneaker. Right. So there should be V. There should be V times V. Okay, times V. But the problem gives you the final result times V already. Okay. MLVS is the unit is not kilogram per day, right? It's milligram per liter. Therefore, you say milligram per liter times V. What is V? Right? That's gram, and not waste per day. Okay. So here there should be V times V. Okay. So that's a typo. All right. So take a look at previous exam papers. Right? They will tell you what are important, right? What are important, right? Some will be tested again, some will not. You have a question? No? All right. Final chance. Right? Yeah, please. I believe. Yeah. It should be. It should have been uploaded. You can actually find it previous years. It's not available. I'm not sure. Available? Okay, good. What does it mean? Okay. All right. So that's it. Okay. Thank you very much for your participation. Um, so remember to complete ESFQ, right? ESFQ.